Okay, everyone can hear me, right? Can you guys hear me?
Yeah.
Okay,
Yeah.
good. Let's get started. Okay. Okay, so today we keep talking about heap-based attacks. So some of them are actually quite similar to stack-based buffer overflow. So in heap-based buffer overflow, we find a vulnerability in the software that has an overflow that we overflow other chunks. So in heap, we have many chunks. So basically we overflow other chunks. But we cannot use something like cookies or canaries to protect a heap because there is basically no return instruction. So you don't have a point in the time to verify if the heap is modified. There has been some new hardware extensions to protect data on a heap, but they are quite new. They just came out in the last 2 years. So today we're going to say some tricks to hack a heap that has been there for decades. So let's say the first example here. So this is a C program, but this C program is very similar to our C++ object. So here we have an airplane structure. So it's a structure in C, so it doesn't really have the virtual function tables as in C++. But we do have a function pointer in the structure. So you can see the structure, the beginning, let's say if this is 32-bit, then there is a function pointer at the beginning, 32-bit, 4 bytes. Then there is a name of this airplane, 20 bytes. Then there is another function called fly. The fly function will just print flying. That's it. The main function will first print out flying and the address of flying, and also print out the address of a print flag. Print out those two address of functions. Then we will create our first structure, plane 1. Then we are going to use malloc to do that. So we just do malloc size of airplane. Then we get the pointer to the airplane. So then from last class, we know that before that pointer, 8 bytes are used for metadata. So as a programmer, you do not really say that directly. What you get is directly is a structure's address. Then we print out the airplane is at that address. Then we create another airplane. Then for both airplane, we assign that function pointer as a fly. So both of them fly. Then we're going to do a fgets, 2 fgets, and you can see when we have fgets, probably there's a software vulnerability. So what we do is for the second airplane, we're going to input 10 characters, 10 letters. So obviously 10 letters will not cause any buffer overflow because the name is, we're going to put that in the name. So we're giving the plane a name. So 10 will not cause any buffer overflow. However, the second one, we're going to write 50 characters to plane 1. That may cause a buffer overflow. Then we are going to call those 2 functions. So let's say how we can exploit this. When we go to airplane heap overflow 1, let's do the 32-bit. So when we do this, you can say it will print out fly is at this location, print flag is at those location. Airplane 1 is here, airplane 2 is here. Then we just type a name. This will be the name of airplane 2. Then we type another name for airplane 1. So you can say it's just flying. There's no system crash, program crash. But if we get a lot of input, then we will get a crash here. So actually, when I input this, I input many characters. The first turn will go to airplane 2's name, and the second one, the rest will go to airplane 1's name. So how do we exploit this? This is, I think some of you already get the idea. It's very simple here. So let's say this is a heap. This is a low memory. This is a high memory. So it's very possible that those two, so here we're creating two malloc chunks, right? So it's very possible they will be adjacent to each other. Maybe there are some padding in between, but still they are adjacent to each other. So airplane 1, we have the previous chunk size and its own size. Then it has the function pointer as its first member. Then it has a second member with the name 20 bytes. Then after that, we may have the airplane 2. So when we do the override, what we do is we override from the name. So we will be able to override the previous chunk size, its own size, and also override the function pointer. So when we overwrite those two metadata items, obviously it will be very dangerous. We will be able to exploit something like this, but for this simple example, we don't need to exploit those two. So we just can put garbage here, not here, the size and previous size. But we can put the function, we can change this one to point to print secret. So after we set the names, well, airplane 1 will call its function pointer. So instead of calling flying, we're going to call print secret. So it will print flag. It will print the flag for us, right? So it's very simple, and the exploit will just look like something like this. Very simple. You just need to calculate the size, which, let's say the example here. So we run this twice. You can say they always have the same size. They always add the same address. So airplane 1 is at B0, airplane 2 is at D0, which means that's how big is that? That's 32. That's 30 B, C, D, right? So that's 32 bytes. So our exploit should look like, let's see if it's correct. So the name is there is, let's see. So from here to here, that's 32. So we just need, oh, actually not from here. Oh yeah, from here to here is 32, but we're not changing this part, right? So we're -2, so we need the 28. So from here to here, we're writing from here. So it's 28 bytes. 28 bytes to here. Yeah, that's correct. So which means we need 28 bytes of garbage. Then we just have the address of print secret, print flag, which is CD 62 55 56, right? So we just pipe this into heap. Oh, it's not working. So we're still, let me get rid of my Slack here. So what's wrong here? 28 is not correct. It's still calling flying.
You had to put in the first
oh, we
first
didn't
name. There's two inputs, right?
Oh, there are two inputs. Oh, yeah. Okay. Yeah, there are two inputs. So we put everything into this one. Yeah, we put into P2. So what we need to do is, oops. What we need to do is, so the first one we just do just garbage, then a new line there, right? So then the airplane 2 will get the name AAA. The airplane 1 will get the new name here, which is this part. Then we overwrite. So, but interesting, you can see that. So when we do not trigger that print flag, we did change the metadata. And because we change the metadata, when that object is freed later, the object is freed here. When the object is freed, free identified that there are some errors, and those are invalid pointers, then aborted the execution. Okay, so now this should work. Okay, you see. So when we do this, this part goes the airplane 2's name, and this part goes to airplane 1's name, and overwrite airplane 2's function pointer. So we were able to the second time. So when we call the function pointer of airplane 1, we get flying. When we get call function pointer of airplane 2, we actually call print flag. So we get the flag. Then after that, this version of the heap management, the malloc we are using, the DL malloc we are using, actually detects there is a double free or corruption. So a further attack is forbidden here. Okay, so that's a very simple one. Let's keep moving to the second example will be use after free. So use after free is a quite serious vulnerability in recent years, in the last decades. So it happens when an object on the heap is freed, but there is still a pointer somewhere in the address space points to that object. But because that object is freed, the data there doesn't make sense. The metadata is already updated by the allocator. So in those cases, we can exploit that to do a lot of very dangerous stuff. And this has been a very powerful exploit for modern software, including web browsers, including those very complicated programs. For web browsers, imagine that how attackers can attack that. Attackers will use something like a JavaScript. Attacker will embed a malicious JavaScript on a website. And when the user visits that website, that malicious JavaScript will execute. But JavaScript is not native language. It technically runs in its own virtual machine. So it has some abstraction there. So it's not really binary code. But JavaScript will create a lot of dynamic objects that will create objects on heap. So to do a buffer overflow on JavaScript is difficult, but to do a heap use after free on JavaScript is much easier. So this is a list I retrieved last night from MITRE. So you can say use after free right now is in this year. I think this is year. This year, use after free is still ranked as a number 7 in all the weakness or software vulnerabilities. So we also talked about others like out of bound write. This is kind of like a buffer overflow, right? Then there are several that are related to web or secure. There's an out of bound read. Then there is use after free. So this slide shows how it works. First, this is our original address space. So we have, so this is low, this is high. We have those libraries, we have executables, and we have the heap and the stack. Let's say we have a local pointer. So it's a local pointer, so it will be the pointer itself will be on stack, but the pointer points to some object on the heap. It will use the function with malloc to create several objects on the heap. Then one of the pointers will point to that heap object. Then we may free two objects from here. From last class, we know that when we free that, the data here is not valid anymore. The chunk size, previous chunk size, and will be changed. And also here we are going to have two pointers to create a double linked list for the chunks. For different implementations, they do not necessarily are double linked list, but some kind of data structure. They can also use tree data structure because tree will be faster. Anyway, in this case, the pointer is pointing to some objects that do not exist anymore, right? So those pointers are called dangling pointers. So they are leftover pointers in the code reference to freed data. And if those data are referenced again, there will be some issues because you don't know what will happen. And attackers can exploit that, can craft clever exploit. So we will show later how we can do that. So also use after free can be so how attackers can exploit this. Attacker, they can create some new data on the freed area. So this freed area, attackers can somehow trigger malloc to create new data, or if there is a buffer overflow, let's say this chunk, this data type has a buffer overflow like what we saw for the last example, then we may overwrite everything after data. Then since we can overwrite this part, then we can write it any way we want. We can make it look like a valid object. We can create the previous chunk size, right? We can make it look like a valid object. So attacker usually has two ways: either malloc a new data structure, or just overwrite this part. But the dangling pointer is still there. The dangling pointer would be coordinator. So how do we exploit something like this? So here we have another example. We have airplane object exact as what you saw just now. It has a function pointer. It has a name. Then we have a new structure called car. Car doesn't have the function pointer anymore. It only have a volume, which is the engine volume for the car. But the type of it's an integer. It's not a function pointer. However, they are both 4 bytes for 32-bit version, right? So no matter it's a function pointer or it's an integer, they are just the 4 bytes. Then the car also has a name. So the main function print out the functions, the car print out the fly address, print flags address. It first create the airplane object, then set the object function pointer to fly, then call that fly function. Now after that, we free this object, okay? So the object doesn't exist anymore in this case. Then we create a new job object, which is a car. And because how malloc is implemented, it's very likely that the car will be placed at the address where the airplane was. Okay, so here we have P here. So in this case, Actually, here we use P1, right? So where is our, oh, P is also here. So let's say after we freed P, we didn't set P as 0. So all good C programmers, if you learn C programming, you know that all the textbook tell you after you free P, you should also set P as 0. Here, we didn't do that. So the P still has the airplane's address, which is not changed. Then we create a car, which is very likely at the same address. So P1 and P, they have the same address, very likely. Then we define a volume and ask you to input the volume. After you input the volume will be set to the object car. So then there is a use after free vulnerability here. So P has already been freed. We should never use it actually, but we are still using it here. So that's why it's called a use after free vulnerability. So in this case, we are basically using the volume of the car as the address of a function, and we are trying to call that function. So if your volume is 10, the CPU will jump to the address 10 and keep executing there. So you will get a segment fault. But if your volume is properly set, then you can actually call the print flag function. Does that make sense? So let's go to heap overflow 2. When we run this program, we first show fly is here, print flag is here. Print flag, I actually print out the decimal number for you, so you can directly input. The airplane is at this place. You can see that after the airplane object is created, we call that function, then we free it. After we free it, we call the car object. See, the car object will be at the same place as the airplane object. So now if we input the volume of the car, we input 500. What will happen? 500 will be used as the address of the function, and we were going to call that function. So we will trigger a segment fault. However, if we input the address of print flag, it's going to give us a flag. Does that make sense? Okay, so those are 2 examples of heap overflow. So next, we are going to see a much more complicated example, but this example has been fixed in the library we are using. It's to exploit this right now on the C library, it will be much more complicated than this. But anyway, so this is a vulnerability in the DL malloc, and it was in the Git C library 2.3. So I believe the library we're using on our server right now is probably 2.36. Oh, we're using 31. Okay, so we're using 2.31. So and the one on my slide is 2.3. It's actually kind of like maybe 15 years. The 0.3 is like 15 years ago, but the basic structure are the same. But you can say we have this. This is from the source code. So this is what a malloc chunk look like. We have this internal size t, which is 8 bytes. Then we have previous size, the size of previous chunk if that chunk is free, and the size of the current chunk. And this size includes the metadata, which is 8 bytes. Then after that, we have those 2 pointers, but those 2 pointers is only used when this chunk is freed. Otherwise, this part is your user's data. We also define a type called malloc chunk pointer like this. So when we say memory or buffer, we mean here after the metadata. When we say the chunk pointer, we mean 8 bytes before the what malloc returns. So malloc always return here. Malloc doesn't return at the chunk pointer. But the library itself obviously use the chunk pointer to access the metadata. So the heap, when a heap is first created, it doesn't really have chunks. It only have one called wideness chunk. And this is the only chunk exists there. Other chunks are created by splitting this one. So 2.3 C library actually also arrange heaps into many different areas and one area for each thread. That's why it has some fast thread support. So what I discussed here today are actually from a book called Buffer Overflow Attack, Detect, Exploit, and Prevent. You can easily get this book online since it has been like at least 15 years old. So when a chunk is freed, the C library will try to consolidate its nearby chunks if its previous chunk or following chunks, they are also free. So basically consolidate them into one bigger chunk and that's a freed chunk. So this ensures that there are no two adjacent free chunks in the memory. So the resulting freed chunk is then placed in a bin, okay? This is basically the doubly linked list of free chunks of a certain size. There are many bins allocator maintains. For the 2.3, there are 64 bins for size 8 chunks, 32 bins for size 64 bytes of chunks. Then if the chunks are bigger, the bins are smaller. But in that bins, there are still many chunks, right? So we have seen this figure multiple times. In this scenario, we have 3 chunks. They are adjacent to each other. Chunk B is already freed. So chunk B has previous size, its own size, and there is also a bit previous in use. This one indicates that its previous physically nearby, the physically previous chunk is in use. Whether chunk B is in use a lot is determined by its next chunk. So the next chunk will also have this size field 4 bytes, and there is a bit called a previous chunk in use, and this one is cleared, which means chunk B is not used, and the chunk A in this case, it is used. Then because chunk B is not used, so it has this forward and backward pointer. The data part doesn't make sense anymore. It's just garbage. We do not clean that, but it's garbage here. So here, chunk A, we're trying to free chunk A. Because after chunk A, chunk B is also freed. So the C library will try to merge those two, consolidate those two to create a bigger chunk. So after this whole part will be a new chunk. So it's much bigger. It will go to another bin. So all those freed chunks, they will be just linked using this doubling link like this, using the forward and backward pointers. So the forward and backward pointers, they do not pointer to the adjacent physical chunks. The previous size actually is about the adjacent physical chunk, but the forward backward are the chunks in the same bin. So they are not really physically adjacent to each other. So if you want to access the physical asynchronous jump, it's very easy. You just calculate this by using your own size. You know this chunk's address, then add this chunk's address with size of this chunk, then you get the chunk address of the next chunk. If you subtract the previous size from this chunk's address, you get the physically previous chunk's address. So this is cleverly designed. You can easily get physically adjacent and also the adjacent chunks in the links. So basically, this is how do you calculate that in the source code. They're just defined as two macros. The next chunk, so P is the chunk pointer of the current. It's basically the chunk address of the current chunk, right? It's not really what malloc returns. It's what malloc returns -8. So to calculate the next one, it's just we just add P's own size because that bit is used or not has nothing to do with this. So we just add the current chunk size to the current chunk's address, then we get the address of next chunk. The previous one is also easy. Current chunk address minus previous chunk's size. And previous chunks, that's why previous chunk size is stored in the current chunk. Then we get the previous chunk's address. Okay, so here is something very interesting, is we are going to consolidate chunk A and chunk B. So chunk B is already freed, right? So chunk B is already in some bin. But now we're going to consolidate chunk A and B, which means we're going to remove chunk B from its previous bin and add the new resulting chunk into a new bin. So how do we remove chunk B, which is freed, from a bin? That operation is called unlink in the same library. So unlink is also a very simple operation, just 4 operations here. So we have 3 chunks here. The bottom is low address, top is high address. We have 3 freed chunks in this case. Chunk A, chunk 1, chunk B, chunk P, and chunk 3. So chunk 1's forward where points to where chunk P is, right? So we're pointed to here. And the chunk P's forward where points to the next one. So they are not physically adjacent. They are just adjacent in the double list. So chunk P's pointer forward will point to the next chunk, which is chunk 3. And chunk 3's backward will point to chunk P. And chunk P's backward will point to chunk 1. So we have 6 pointers here. And unlink will remove this chunk from this link. So you can imagine after remove, what we should do is chunk 1's forward should point to chunk 3. Chunk 1's backward, we do not care here because it should point to someone at a different address. Then chunk 3's backward, instead of a pointer to chunk P, now it should be changed to chunk 1. So that is what it should look like after we remove P from this double link. So this is actually the source code from the C library. It's also just a macro. Unlink is just a macro. So this macro actually only take only one parameter, which is P. It's the chunk you want to free. You want to unlink in this case. The BK, FD actually they are not input. They are input and output. They're output. They will be used later. Okay. So let's say the first line of code here is we set BK as P, the backward chunk. So now BK is a pointer. BK points to where P's backward points to, which is chunk 1. Then after that, forward points to what P's forward points to, which is chunk 3. So we set BK and FD. So after that, FD, the forward backward, which is chunk 3's backward, will be updated as backward, BK. So we change this pointer from here to here, okay? We also change the backwards, the BK's forward from P to chunk 3. So this pointer is changed to here. So after that, we removed this object, this item from the double link. So if you took data algorithm or data structure class, you probably wrote code like this, right? Very simple. So why this is interesting is because we are attackers. And as an attacker, we always think this is a piece of code written by the C library developer. But looks like this piece of code can be exploited. There are vulnerabilities in this piece of code, those 2 lines. Why is that? Because what we're doing here is basically, let's say as an attacker, we control the chunk P. Somehow we can overwrite the chunk P's forward and backward pointer. Then we can override it to anything we want. Then whatever is put in the forward here, that forward address plus 12 will be updated as our backward address. Does that make sense? We have that 12 because so previously this forward points to here. But we're going to overwrite this object's backward pointer to our own backward pointer. So this part will be updated by this part. And this part's address is determined by this one. Okay, so which means the third line of code here, this gives us, if we can control FD and BK, this gives us an arbitrary write vulnerability. We can write anywhere in the address space any value we want, and we're not going to so what do you want to overwrite as an attacker? You want to overwrite some code pointers in the address space, right? So the first half of the class, we always try to overwrite the return address, which is one code pointer. But there are many other code pointers we can overwrite, like the global offset table of a L file. There are many function addresses. We can overwrite that as well. So this vulnerability here actually give us an arbitrary write vulnerability. So how can we actually pull this off? We need to look a little bit deeper into the free algorithm. Like I said, this is harder to pull off now because the library has been updated many times. But for that version, it actually works. Right now, we don't have that version on our server, but let me say if we can downgrade our system to do that later. So first, let's understand the free algorithm. First, when you do free 0, will not do anything. The free algorithm will also check if the chunk is created by memory map, not created by malloc. So if it is created by memory map, it should not be freed. It should be released by memory unmap. Those two are system calls. Malloc are not system call. Malloc are library functions. So we usually only use memory maps for a large memory region, like a page, something like that, or much bigger. So if you remember in our share code development class, I showed you how our sanitizer or share code, what is that called? What did we call that? Anyway, it will read your share code, place your share code in the memory and execute that, right? So that memory region was created using memory map. So it's actually on the heap, but it's directly, we ask for the memory from the kernel, not using malloc. So free will not handle those memory regions, so it doesn't matter. Then also if the chunk we're going to free is next to the wideness chunk, which is a huge chunk, then it will be merged into that chunk. So it will not be placed in any corresponding bins. It will just merge into a huge chunk. So all other chunks, if they do not match those three conditions, they will be and sometimes they could be consolidated. But when they are consolidated, they will be placed in the corresponding bins instead of the wideness chunk. So when they placed in the corresponding bins, they have to be unlinked from its existing bin. And we saw that unlink code has an arbitrary write vulnerability we can use. So go back to this example. Let's say how we can do this. So we have chunk A here. This A is going to be released, and because chunk B is freed, we are going to merge these two. And because we are going to merge these two, chunk B will be unlinked from its existing bin. And we want to exploit that. So here we assume the chunk A, this object has a vulnerability. We can do a buffer overflow here. So let's say chunk A is our airplane object structure. So when we overwrite A's name, we will be able to overwrite everything after this. Then this figure shows how we should construct this attack. So this is before overflow, what it looks like. After overflow, we are going to create two fake chunks here. The reason we create fake chunks is we want to have our own forward and backward pointers. the forward pointers determines where we are going to do this arbitrary write, 12 bytes off. The backward pointer determines what we are going to overwrite. By combining them together, we can write to wherever we want. So we're going to create two fake chunks, and let's call it F1 and F2. So F1 will look like this. It has previous size, which the size doesn't really matter, but we can actually get from the size of A. Then it will have its size of itself. Then have a forward pointer, backward pointer. Then we have to create another chunk here because we need to net unlink beneath this chunk is a freed chunk. And whether this chunk is freed is determined by its next chunk, the physically adjacent next chunk, using this flag, right? So that's the previous in use flag. That's where we create another chunk, F2. F2 has the previous size of F1. The size of itself doesn't matter. What matters is the flag here, where the previous in use will be cleared, which means this part is a free chunk. So after the forward, backward, doesn't really matter. We're not going to use that. Okay. Then after that, that's what our exploit looks like. So forward, we'll have the address we want to overwrite -12. Backward, have the address, have the data we want to overwrite. Okay, does it make sense? Oh, looks like there are several questions. Why doesn't it have to be, Victoria asked, why doesn't it have to be written as an address? Oh, Victoria, can you, I do not get your question.
That was relating to the other flag that we were catching, where you had to give the volume and you had the address of print flag. But I realized, well, Jeff told me it was an integer form.
Oh, you're talking about, you're talking about this one, right?
Yeah.
So you're asking, why doesn't it have to be written as an address? So because the car object doesn't really have a address member, the car object only have an integer member is a volume. So when the program asks for input, it is asking for a volume input, not really an address.
And it just interprets it, and it interprets that as the address of the print flag.
Okay. It will be interpreted as the airplane's address.
Okay, that makes sense.
Yeah.
Thank you.
So Jess asked, oh, so Jess, you basically answered that question. Okay, cool.
Yeah, sorry, I just didn't want to talk over you.
Okay, yeah, it's okay. Sure. Okay, so that's basically our heap exploitation part. There will be challenges in the final for heap, but it will be not as difficult as this one, and this one may not work anymore, actually. So I want to say that in our class, we are still looking at the C library heap. The kernel, the Linux kernel also has its own heap. The kernel has its own kmalloc function, and they also have all kinds of vulnerabilities like this. And they have been, in the last 5 years, those vulnerabilities has been exploited a lot in real world. So if you are interested in those, I can send you some papers to read, some exploit to read. Okay, so any other questions for the heap part before we move forward?
Yeah, Professor. Can you hear me?
Yes.
So I'm wondering, like in this graph, is that on the top is the high address or the low address?
This is low address.
Oh, so the top is low address and the bottom is high address. Okay,
Yeah, you
got it.
you can for example, the previous size is at the top, then size, right? So that means this is a low address, this is high address. Yeah.
Okay. So in this case, is the low address on the top?
Yes.
Okay. Got it. Thank you.
Cool. Let's move forward to our. This will be our last topic of this class. Actually, we are going to move down a little bit. Not only software vulnerability, we are moving to micro-architectural vulnerabilities. We will start from cache side channel attack, then talk about meltdown and spectral. Next week, I'm going to show you the demos, and you are going to do some experiments on meltdown and spectral. So how many of you heard about meltdown and spectral? They were like very hot like 5 years ago. They were discovered like 5 years ago. So all our CPUs that time, almost all our CPUs that time were found. Some AMD was not affected. All our Intel CPUs, ARM CPUs were found. They have those kind of vulnerabilities, and those vulnerabilities has been there for decades, and no one discovered. So they were based on all kinds of software vulnerabilities and also side channel attacks. And side channel attacks has been there for like 15 years. Has been very useful in real world attacks, but no one really bring everything together and come up with something like a meltdown spectral. Okay. So in the last 4 decades, basically the speed gap between CPU and our main memory is getting bigger and bigger. Our CPU are moving very fast. DRAM are also getting faster, but still not as fast as the CPUs. So obviously the ideal memory storage system should be very fast as the CPU, very large, and also very affordable. Unfortunately, in reality, we do not have such memory and storage systems. Usually, fast storage systems are very expensive and very small. For example, in the CPU, we can say the registers, they are also storage, right? Those registers are very small. They are basically part of the CPU. They are SRAM, so they are very expensive. Then DRAM are much bigger than SRAM, but they are also much slower. Then we also have HDD. We also have other kind of hard storage. They are huge, very affordable, but much smaller, much slower. Okay, so obviously, the strategy to handle this trade-off between speed, cost, and capacity is to bring faster memories closer to the CPU, and also keep frequently used data and code in the faster storage. So we do not have to resort to those slow storage very often. That's why our memory have different layers. We have a hierarchy. The first layer, we have SRAM on the CPU. Even the SRAM on the CPU, we will say later, they have different levels. After that, we have the main memory, usually it's DRAM. Then we have our hard disk, right? So the storage on the CPU, the SRAM, usually we call them the CPU cache. So that's quite a small amount of storage. They are very fast, also very expensive because they are SRAM. They are part of CPU. And those SRAM, those cache they are between the CPU, the calculators, those computing units, and the main memory, the DRAM. The cache keeps a copy of the most frequently used data from the main memory. So when the CPU wants that piece of data, the CPU doesn't have to get that data from main memory, which will be slow. The CPU will get from its cache, which is on the same chip. That's why it's very fast. So here are some data for access time. I don't know how accurate this is right now because this is like 10 years data. So cache made of a SRAM, the access time is like 0.5 to 3 nanoseconds. The dynamic RAM, DRAM will be 50 to 70 nanoseconds. That's like 100, 200 times slower. Then flash will be 5,000 nanoseconds. Then magnetic will be even 5 million, right? So you can see the access speed is much different. So when the CPU try to access some data, it will first ask cache for that data. If that data is really in the cache, then we call that a cache hit. So when a cache hit happens, it's good, it's fast. But if that data is not in the cache, the CPU has to retrieve this from the main memory. That is called a cache miss. So the CPU we are using right now, the cache hit rate is very, very high. It will be much higher than, it's something like 95%, because it has all kinds of algorithms to optimize that. And because of those optimization, they can be used for side channel attacks. So like I said, even the cache itself has hierarchies. There usually is L1 to L3 cache. For the desktop CPUs, we're using Intel CPUs. Usually there are 3 layers from L1 to L3. For the phone CPUs, ARM CPUs, usually just 2 levels, L2, L1. L1 cache is obviously closest to the CPU. It's basically physically closest, okay? You can imagine CPU is already very small, but even that small distance will make like nanoseconds this difference there. So L1 cache usually is divided in the data cache and code cache. So code cache will only store the instructions, the code. Data cache will store data. So basically we can split the control and the data channel. So that's very good design, but would be a little bit more expensive. Usually L2 and L3 caches, they are unified, which means we store both data and code there. So this is a picture of a very old CPU. This looks like a RISC CPU because you can see there are load store units. Usually RISC CPUs have those units. You can see this is a whole CPU. This is the map of the whole CPU. And you can see more than 50% of this CPU is actually used for cache. The execution unit here is very small, like only this big. Store, node, small, FPU, small. There's a lot of cache. So this huge part is the L2 cache. This is 1 megabyte. This is a very old CPU. Then here we have a data cache. This is L1 cache. This is instruct cache, also L1 cache. So you can see physically, those 2 cache are closer to the execution unit. L2 cache is further away, but L2 cache is much larger. So you can say, I would say maybe 60% of those resources on CPU are actually used for cache. Even though we always think the execution unit are the most important ones, but most of the areas are used for the cache. Or here also we have MMU, the memory management unit. The memory management unit usually also have its own cache for address translation. this is another CPU. This is Pentium 4, so which is also 20 years old. Yeah. Yeah, this is also 20 years old CPU. Yeah, this is a CPU basically. I went to college like 2002, and this is the CPU that time we have, and you can say we have some cache areas. Here we have L2 cache, two L2 cache. Then there must be other caches somewhere. Where is L1 cache? I cannot find it here, but there are other cache areas. Okay. Oh, here, this maybe look like cache. Yeah, this is a TRB cache, which is, if you took the OS class, you know, the look aside, translate look aside buffer. That's part of the MMU. So MMU will translate virtual address to physical address. And the translation table is very big, and every process will have its own translation table, right? So the translation table can only be placed in the main memory because it's big. Then the translation happens all the time. When you fetch an instruction, you need to translate that instruction's address to physical address. That instruction use other virtual addresses. Then you need to translate those addresses, right? So to make that faster, the MMU has its own cache, which is the translation look aside buffer. Basically, what it is recently translated, it will put in the buffer because it's very likely they will be used in near future. Here is a more recent CPU. You can see this is an 8-core CPU. And each core has its own L1 and L2 cache, which are not labeled here. However, they share the L3 cache, which is a big area here. MMU is here. MMU has its own cache somewhere. So some of this, so maybe this part, or maybe it will be some part look like this inside of this, that will be cache. So maybe those are L1 and L2 cache. So then there are IO modules. So you can see that cache is a really important part of a modern CPU. So for efficiency reasons, multiple words or multiple bytes combined together, we call it a cache line or cache block. So one cache block is moved at the same time. We cannot move just several bytes of the cache line or cache block there, because you can see if the granularity is too high, it's actually means you are going to make a lot of retrieve from the memory. So do not necessarily make the system faster. That's why for most CPUs we are using right now, a cache line or cache block is 64 bytes. So the adjacent 64 bytes, aligned also 64 bytes, they will be, if one byte is moved into the cache from the memory, the whole block, 64 bytes, are moved into the cache actually. And also our cache, right now, the cache we're using are called the n-way set associative cache. I will try to explain them as simple as possible so you can understand those concepts. So for any given cache line or cache block, 64 bytes in the main memory, they can be cached at several locations. They cannot be cached at every location in the cache. First of all, cache is a much smaller storage than the main memory, right? So the CPU I'm using maybe has 2 megabyte cache, but my DRAM, my main memory is 32 gigabyte. So cache is much smaller. So obviously we cannot put everything in the cache. If we put everything in the cache, we do not need the main memory. But for any block or line, we want to organize them in a cache. And usually there are uncached lines in a cache set. We can put those data. I'm going to use a little bit more animation later to show you that. So let's say we have a 32-bit version computer. Then that 32-bit address can be divided into 3 parts. The last part is the offset inside one cache line. Since one cache line is 64 bytes, which means we need 6 bits for offset, right? So those least significant 6 bits are used for offset to find out which specific byte it is in one cache line. Then the middle, let's say we have a 32 kilobytes 4-way set associative data cache. Then in this case, the number of sets we have is a cache size divided by the number of ways times the line size. The line size, number of way, in this case, we have 4 ways cache, which means we have 128 sets. So each memory location, when brought to a cache, it can only go to one specific set of cache lines, but it can't go to any cache line in that set. So let's say one more, this example would be better. We have 100, so we already said we have 100, hold on. We have 128 cache sets here. So each row is a set in this case. Each row is a set. And the set is labeled from 0 to 127. And that is the middle part of the address. So given any address, we know that we get the middle part of that address, then we know if this byte in this memory is going to the cache, it should go to this set, okay? The 128 set. Then in each set, there are 4 different items, different, we can call it 4 ways or 4 cache lines. It can go to any of those 4, okay? Then the higher bits is called a tag. Those tags are stored in the cache as well. So let's say we have an address here. That address can go to this set, which is this row. It can go to here, it can go to here, 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 doesn't matter. But it cannot go to a different set. For a specific address, it cannot go to a different set here. So what do we actually store in the cache? Include the data itself, which is 64 bytes. We have the tag, which is this part of the address. Because eventually we want to, if the data is changed, we need to write the data back to the main memory. From where the data is, we know the set number. And we don't care about the offset when we write back. But we still need the higher, most significant bits of the address. And that is stored with the data. Then there is a valid bit to say if the cache is valid or not, which means if the cache is in use or not. Then there another one is a dirty bit. So the CPU brings some data from the main memory to the cache. The CPU does a lot of operations on the data, so the data can be changed. When the data is changed, the CPU do not necessarily immediately write the data back to the main memory because that will be slow. the CPU may just keep this data in the cache, do not write it back to the memory, and simply change a dirty bit, which means this data has been changed. If there is a lot of core CPU wants to use this data, and that data in the memory is not the latest version, then this CPU should write the data back to the main memory. Or actually modern CPUs, they can directly retrieve the data from a lot of cores cache, doesn't have to retrieve from the main memory to make things faster. Yes, there are a lot of research going on in the computer architecture level to make things faster. Another important concept here is called the congruent address. So each memory address, obviously, if they bring to memory, if it is brought to memory, it can go to one of those. It can only go to one of the cache sets, right? So the memory addresses that map to the same cache set are called the congruent address. So those congruent addresses, they compete for the same cache lines in the same set. And we need replacement policies to determine which lines should be replaced. So going back to the figure here, the congruent addresses are the addresses which this part, the bit 6 to bit 12, they are the same. Doesn't matter what the tag part they have. As long as the set part are the same, then they are congruent address. They compete for the same cache sets there. So because cache is very small, you bring new data in, you may need to remove old data. So there are different policies to replace the old data. Mostly, I think Intel CPUs use either least recently used policy or least frequently used policy. But the ARM CPUs, especially low-end ARM CPUs, just use a random policy. Obviously, the least frequently used policy or least recently used policy probably are the best policies. But it also means your CPU will be more complicated. So the least recently used, which means at least you need to remember which cache lines were recently used, how recently they were used. Least frequently used, you even need to record the number of times a cache line is used by the CPU, right? But a random policy doesn't need to care about that. So it will be easier to implement, but not necessarily, the performance not necessarily better. Okay, so we are attackers. We are interested in how do we exploit those policies, exploit this cache to do attacks. So the attack we are interested in is called cache side channel attack. So side channel attack utilize time differences between a cache hit and a cache miss to infer whether specific code data has been recently accessed by the previous piece of code, by another CPU core, something like that. If it's a single core CPU, obviously you can only access the previous piece of code, what it accessed. But if it's a multi-core CPU and the cache is shared, like I showed before, the L3 cache is shared, the modern CPUs, then you can access what other cores has been accessing. This is actually very scary and realistic because, for example, you use Amazon. In Amazon, you have your own virtual machine, and your virtual machine and someone else's virtual machine run on the same physical machine. So those two virtual machines, they may share the L3 cache. And if an attacker can somehow place his virtual machine on the same physical machine with your virtual machine, then your virtual machine does all kinds of encryptions. The attacker's virtual machine can use the cache side channel to infer your crypto keys. that has been demonstrated in the last, I would say 15 years. It's actually possible. I also do some research in this area. We use cache side channel attack to break the security guarantees of trusted execution environments. So here is how the cache side channel attack works. I'm using ARM as an example. So here we just have one ARM instruction. This is a load instruction. This node, so the first operand is the destination. The second is the source. The destination is register R1. The source is the memory location. The address is in R0. So R0 is a pointer here, right? So before you learn cache, this is what you imagine how things work. We have those CPU registers. This is so far what we have been doing in this class, right? We're only looking at registers, we're only looking at memories. So far in the class, we're not thinking about cache. So let's assume R0 has the value 3000 hex. Then at 3000 hex, we have the data 1 here. This is in memory. Then we're trying to load this data into memory. So before this class, what we believe is this data 1 is moved from memory to the register R1, right? That's a simplified model. What actually happens is there is also a cache. When this instruction is executed, the CPU will not directly access the memory. Instead, it will ask the cache, do you have the data at memory location 3000? If the cache has that data, the CPU will directly retrieve from the cache. It will not talk to the main memory, which will be very fast. Otherwise, the CPU will ask the cache to retrieve the data from the memory. So the data will still move from memory to the cache. Then the CPU will retrieve that from the cache. So you can say this step is additional, so which will be much slower. So let's assume as an attacker, we can measure the time before, what is the current time before this instruction is executed, and after this instruction is executed. Then we can calculate how long it took for this instruction to execute. Then we can infer whether, so we can know whether the data in address 3000 is already in the cache, right? So if it's already in the cache, it means someone before me has been using this. Before this instruction has been using the data in the cache. So in the last 15 years, many attackers, many researchers have come up with many different attack primitives for cache side chain attacks. I also come up with one, but it's not very popular. We're publishing a paper. Anyway, so you can see they all have very catchy names. Evict plus time, prime plus probe, flash plus flash. Those are very catchy names, but do not necessarily mean those attacks are just 2 steps. Okay. Some attacks are more complicated than others, but they always come up with a catchy name. So I will use several examples here. The first one is called evict and time. That's probably the first attack primitive come up designed. So you can say that it was 2005. So it's almost 17 years ago. So that's kind of like the first one. So it was published in the same paper as prime and probe. Actually, prime and probe has been quite popular in the next few years. So evict and time, the approach is very simple. The attacker will first measure the execution time of a piece of victim program. Then it will evict a specific cache set. Then it will measure the execution of the victim program again. So if the second time, the execution time is slower, which means the victim has been bringing, the victim program has been bringing some data to that specific cache set, right? To bring that to the cache set from the main memory. That's why it's slower. It means the victim program has been using some data or executing some code at some specific address, right? So the victim program and the attacker's program, they can be just sharing the C library in this case. They are sharing C library. So the C library is, there is only one copy of the C library in the main memory. And the attacker will victim some cache set. For maybe that cache set maps to several instructions for some specific calculation. Then evicts all of those. The victim program runs, it uses those instructions again of the C library. So it has to retrieve those instructions from the main memory, which will be slow. Then the attacker will know that, oh, the victim has been using those instructions. Those instructions may be after some predicate. Then the attacker can know, okay, this predicate is true or false, right? Then another attack has been quite popular, very robust, is called prime and probe. Prime here obviously means get prepared. So let's say this is the attacker's address space and the victim's address space. So in this attacks, we assume attacker and the victim, they have their own process. In the example we are going to see next week, actually, we will use the same address space to simulate this. Just one process to simulate this. So the first step is the attacker will get one cache set prepared. So how does the attacker do that? The attacker will keep reading some congruent address, its own address space. So those data from those congruent address will be brought into the cache. The attacker will do that many, many times. So hopefully he can fill the whole cache set. So the whole cache set has attacker's data. Then the victim program will run. If the victim program will use some concurrent address in its own address space and brought into those cache locations, then let's say those two data is brought into cache and replace the attacker's data. Then the third step, the attacker will try to access those different memory locations in its own address space again and measure how long does it take to get those data. If the data is, so you can imagine those two has not been replaced, the attacker, when the attacker measure that access, it will be very fast. Those two has been replaced, then will be very slow. The attacker can infer that the victim has been using those addresses. Another approach, flush and reload, is also similar. So in this case, we assume a memory block is cached here. Then attacker will try to flush this memory block. This one actually requires the CPU to provide a flush cache line instruction, which is provided in recent CPUs. But when we do prime and probe, say we're not doing the cache line level, we're only doing the cache set level. So the attacker will try to flush a specific memory block out of the cache. Then the victim may access that block again. So when the victim accesses that block, it may go to any of those sets, right? Not necessarily go back to here. You may go to a different cache line in the same set. Then the attacker will access that block again, but it doesn't have to be at here. As long as it's in a cache, it will be fast. Then attacker will measure if this specific cache block has been used. So this is a more fine-grained attack. Okay. By the way, I forgot to mention that in the final exam, we're not going to have cache side channel attack exploit challenges, but you do need to finish the homework to do the cache side channel attack challenges in the homework. Now, any questions for the background knowledge part? There are a lot of concepts. So everyone is following? So David is asking, what does knowing what address do for us? Okay. So imagine the victim is running an encryption algorithm like AES, right? So AES has a lot of sensitive data, like they call it S box or T box. So those are, in those boxes, those are predetermined hard-coded data to do some data calculation. And which item in the box to use is determined by the crypto key. For example, if the third bit of the key determines we should use 56 item in the S box, something like that, right? Then attacker can infer which items in the box has been accessed, which means which item in the box has been used. Not necessarily very accurate, but get a rough idea what has been used. Then can reverse what is the crypto key in this be used for AES. This can make the hacking the decryption much faster. You do not always use the cache because it's a side channel. It's not that reliable, right? But still, you can make the attack much easier. Okay. Next, let's say one example here. This example is developed by a professor from Syracuse University. So we're going to use the seed lamp for this, for those cache challenges. We haven't put this on our server because it's quite complicated, because our server runs in containers and the container runs in virtual machine, and there are multiple virtual machines run on our server. So sometimes things are not very reliable. So we haven't fully ported this to our server. So this year we're still going to, I will send you guys a virtual machine, and you will use a virtual machine on your own computer to do this. Let's say here we have a global, we have a global variable, which is an array. The array is huge. So it's 10 pages each. So this is for the entire CPU. So each page, oh, by the way, if you are using the latest ARM CPU, for example, you are using M1, M2 Mac, I'm not sure if it works. Last year, we had a lot of issues. Some students have M1 CPU and they find the cache side channel do not work. So in those cases, you can either borrow your friend's computer to do this, or you can still try this on your computer and just faithfully record what happens, but it may not work. Yeah.
Professor,
Yeah.
I know that for 365, Ken Smith set up Seed Lab VM online. I have an M1. I think you email him, maybe he can set it up. I don't know how long it takes though, but I have a Seed Lab VM for 365.
Okay. Yeah, how about this? Let's try to set this up on our server because we use Intel CPU. But we do not really guarantee it works. Yeah. So in our server, we do not need to use a lot of VM. We just use our compiler, our container. Yeah. So I do not know if setup in Ken's machine will work either, because this one is related to CPU. It's quite complicated. Anyway, thank you for the suggestion. Let's look at the code here. Now we have a global variable array, which is 10 pages. Each page is 4K here. The main function, we have a local variable junk. Then we have 2 local variables, but we tell the register, tell the compiler to put those local variables in register instead of memory. Those are time 1 and time 2. So from the name, you can see we're going to use that to record the time. Then there is a pointer to point to address. Then there is another integer I. So first, we initialize the global array. So we're basically initialize each page. We have 10 pages, initialize each of them. Then we flush the array from the CPU cache. So we use a library function mmcl flush. So the instruction eventually get is also called cll flush. That's the entire instruction to flush a cache line. So we are going, so this function take the address as input. So we're getting, so basically we are just using the very first block of each page. Each page is 4K, 10 pages, but we're only using the first block, which is 64 bytes. We are flashing it out. So here we initialize that. This may bring that block into the cache when we initialize this. Now we make sure we flush them out so they are not in the cache. So after we do this, we know that those 10 items are not in the cache. Then we're going to access some of the items. Let's do, in this case, we to access 2, then access 8, okay? We're going to set a value to that. So that value, so we're going to bring that value, we're going to write 200 to that memory. And because this is a write, it will also bring, not only read, but also write, will bring the data from memory to cache. Then after that, we are going to measure the time we access those 10 different blocks. So we just get the address at the beginning. Then we get a time. What is the time now? the junk doesn't really matter. This is a real time. This is also mapped to a CPU Intel CPU instruction to get the current time, a very accurate one. So you can see to get an accurate CPU time, you do not need kernel privilege. User program can do that. Then you are going to access that address. So here we're not writing anything, we're just accessing. Then we get the current time again, then we measure the time difference. So you can imagine what it will look like will be 0 will be very, so we're accessing 10 different addresses. Let's say index from 0 to 9, right? So 0 will be slow. 1 will be slow. 2 will be fast because we bring that to the cache. 3 to 7 will be slow. 8 will be fast. 9 will be slow again. So that is what we expect to see. Next week I'll show you the demo. You can see that it's not always very accurate. So that's why sometimes you do this multiple times. You do many times and just get the average. Because this is side channel. We talked about a lot how the CPU works at the microarchitecture level, but those are information we get from publicly available documents. So how a CPU is really implemented, only Intel and ARM or those vendors, only they know, right? We are only observing. We are still treating in like a gray box, not necessarily a black box, but a gray box. So that's why sometimes there are still a lot of noise, a lot of results. We cannot explain why, but if we do the experiment many times and get an average, the results will be a little bit more consistent. So for this one, we have to compare this use cache time. Use architecture native. So let me ask the TA try to do that on our server instead of directly using the VM this week. Also, by using LS CPU, you can see the cache settings of your even in our server. If we do a CPU, oops, CPU, you can say what CPUs we are using, how many cache lines it may have. Let's say the CPU on our server is so the 32 cores, and the CPU hertz, and also you can see the cache. So L1 is a data cache, 1.5 megabyte. L2 instruction cache is 1 megabyte. L2 cache is huge. It's 40 megabytes. L3 cache is 1.3 gigabytes, right? So we have a very powerful CPU in our server. And you can also say, I mentioned that there are spectrum and meltdown attack, right? So those are new information included in the last 5 years. You can see that they say meltdown not vulnerability, meltdown not affected, vulnerability spectrum, there are mitigations. So if you check my local CPU, you can see that I have an 8-core CPU, and my L1 data cache is only 192 kilobytes. L1 instruction cache is 128 kilobytes. L2 is only 2 megabytes. L3 is only 8 megabytes. So you also need to do this on your own CPU as your homework, and also from your CPU models. I want you to, so you can get a CPU model. From there, I want you to search more detailed information of your CPU, like how many sets are there, or how many ways are there. Use information you can calculate. Well, maybe one of those, sets or way. Then use information you can calculate how many sets you have or how many ways your cache has. Okay, next we talk a little bit about the meltdown and the spectrum attack vulnerability, which were discovered 5 years ago. So a lot of you remember this vulnerability, those two? Anyone remember this? A lot of you remember that.
Yeah,
David, you remember that?
Spectre in particular.
Yes, yeah. So yeah, because Spectral is more practical than Meltdown. Yeah. So those two vulnerabilities were discovered by some researchers from Google, Georgia Tech, I believe, and also Grants Institute of Technology, University, and also there are 1 or 2 independent researchers actually. So they published 2 papers, one published in Usenet Security, another in Auckland, I believe, IEEE Security and Privacy. So before those 2 papers were published, they were actually disclosed this to all the CPU vendors. So Meltdown allows attackers to read arbitrary physical memory, including kernel memory, from an unprivileged user process. So this is very scary, right? Because for the last 40 or even 50 years, the CPU vendors are trying to bring isolation from the user space to the kernel space. And at least at the CPU level, everyone thought it's quite secure. The user space cannot get anything from the kernel space, except you have to, if you want to talk to kernel space, you have to make system calls. It turns out the CPUs we have been manufacturing for decades have that vulnerability that the user space program can read arbitrary memory location from the kernel space. So this one utilizes cache side channel, and also another optimization is called out of order instruction execution to leak the information through cache side channel. So a thought process here is any optimization is trying to make the hardware faster than before. And because it's faster, it leaves some side channel, some trace that we can detect. In this case, we use cache to build a covert channel to send out the data. And that's use cache side channel. But the problem itself is actually out of order execution. So Meltdown has been patched in software with Kaiser and KPTI. I remember Kaiser is related to address space layout randomization. Kaiser is basically kernel page table isolation. So that can stop Meltdown there. So let me explain a little bit what is out of order execution. First, what is in order execution? This is like what you learned from your computer architecture class. So the CPU has different modules. We just saw that. There is a fetch module, there is decoding module, there is execution unit, there is read and write unit. From the picture I showed you before, you see that they are actually physical unit inside the CPU. So, and the CPU, we have a pipeline, right? So when part of the CPU, like the fetch unit, fetches the instruction from the memory, the decoding unit is not wasted. The decoding unit is not waiting for the fetching unit. The decoding unit is decode what was fetched in the previous CPU cycle. Then the execution unit may be executing the instructions which were fetched a long time ago. Then after the instruction is executed, we need to write things back to the registers and back to the memory. Those are done by different units. So different instructions, they will cost different CPU cycles, especially for Intel CPUs, because they do not use a RISC architecture, use a complex instruction architecture. Some instructions are much more complicated than other instructions. So in this class, you already see many instructions. You see some of them obviously very easy, just retrieve from, just add something in register. Some of the instructions are very complicated. Yeah, it's going to pop something from the stack, then change the stack, something like that, right? So, so a problem here is if we only execute instructions in the order it comes in, we may waste some CPU units. At some CPU cycles, some units may not have anything to do, and we do not want to waste that. We want to make the CPU run faster. Let's say here we have two examples. The first one, the left-hand side, we have 5 instructions. The first instruction is multiply an integer. We multiply R1 and R2 and put the data into R3. Then the second one, we are going to add the value of R1 to R3, and the result goes to R3 again. After that, R7, R6 moved and to R1, then another multiply. So the right-hand side, you can say it's different code. We load R1, well, it could be memory location in this case, to R3. Then we add them together, R1, R3 together. Then the rest of the code, they will be the same. So obviously those instructions, they have different functionality. But from the computer architecture level, the first AND instruction, this AND instruction stores the whole pipeline because it has to wait for the result of this instruction. When this instruction is not done, we cannot execute the second instruction. The same thing here, right? Because the latter instructions, they are dependent on the previous instructions. Okay. So even if you can say those 3 instructions, they're not related to the first 2 instructions. If we execute those instructions in order, those instructions, they have to wait for those first 2 instructions to finish, which will be slow. So the optimization idea we want to have is the CPU will execute those 2 instructions. At the same time, the CPU will have some execution units to execute the other instructions because they are not related. Here, go back to this figure. Let's assume the CPU only have one fetch unit, one decode unit, but it has many execution unit. So some of the execution unit can be executing those instructions. Some of them will be executing those instructions. So we do not waste those execution unit. Then the CPU will run faster. And this optimization technique is called out of order execution or dynamic instruction scheduling. So obviously the CPU do not strictly follow the order of the instructions. The CPU, so you can say the CPU is not that faithful in this case. So the idea is to move the dependent instructions out of the way of the independent ones. Then we can executing them at the same time. So here is another example. This one is the in order example. The other one is the bottom one is the top one is the in order example. The bottom one is the out of order example, and they are using the same 5 instructions here. Let's say each column here represent one CPU cycle. So fetch will cost one CPU cycle. Decode will cost another CPU cycle. And we only have one fetch unit and we only have one decode unit. So which means at each column, there can only be one F. Okay. And so in this case, we actually also have only one execution unit. So the first instruction you can see here, the multiply. The multiply will cost 4 execution cycles. So this instruction in total will cost how many? Will cost 8 CPU cycles. So when the first one is executing, when the first one is executing in E here, the second instruction will already finish the fetch and decode, but we don't have an execution unit. So we have to wait until the first instruction to finish, then we can keep executing. So you can see that in this CPU cycle here, we are wasting our fetch unit and decode unit, and also read-write unit, right? We're not using them. So they are wasted. Then the third CPU cycle, the same thing. The third instruction still need to wait for 3 cycles. Also, the last instruction need to wait for 4 cycles here. So you can see to execute those 5 instructions, in total, we will need like 16 CPU cycles if we strictly follow the order of those instructions. So if we use out of order instruction, the CPU is not more powerful than before. It still only have one execution unit. Okay. Without adding more execution unit on the CPU. But when the first instruction execute, we do the same thing. The second instruction execute. The second instruction will need the result of the first instruction R3. So it cannot execute. After F at FFD, it has to wait. Okay, it doesn't have execution unit anyway. So it will wait. However, in the fourth CPU cycle, even though the second instruction is still waiting, we can use the decode unit to decode the third instruction, and also execute. Actually, we have two execution units in this example. So we're adding one execute. So you can see here, the third instruction is executed before the second instruction. The second instruction is still waiting. The third one is executed. That's why it's called out of order execution. And because of this optimization, the CPU will be quite faster. Previously, we have 16 cycles. Now we are only using 12 cycles. That's 25% faster. Okay. So those smart guys figured out we can exploit this optimization feature. And this is what the attack, the code look like. Let's say here, this is what the kernel module. So we're going to steal some data from the kernel. So the kernel module looks like this. So there is just a global variable secret. The secret has some data, just a secret. Each byte has a character. So that is a secret where we're trying to steal. Then the kernel module will expose two system calls. One is the open system call. We have been using open for a while. This is how you implement open at the for your kernel module. And also there is a read, I believe. Yeah, you can see this is open, this is read, there is a airseek and also release. So for each kernel module, to your user program to interact with the kernel module, you make the system calls. So these system calls has predetermined names, right? Predefined names like open, read, close. But when you really open that module has to run its own code. That's why in the kernel, you need to specify when there is an open system call to my module, this is the function I'm going to execute. When there is a read system call to my module, this is a function I'm going to execute. Or there is a airseek, this is going to execute. Then the kernel module doesn't have a main function. The kernel module only have kernel module only have its own initialization function, which is declared using module init, and also there is an exit function, module exit cleanup. So you can see the init function here where use print k. So this is a kernel print. In the kernel, you cannot use printf because printf is a C library function for userland program. So print k is for the kernel to print to its own message buffer. The print k will print out the secret's address. We're going to steal from that address. So in this case, we need the address. Then it will, so you can see the secret here. Then it will malloc. It's using vmalloc. So in kernel, there are two different malloc. One is kmalloc, is a vmalloc. Kmalloc will be in, so it's two different heap basically. I don't remember all the details there. Anyway, so we create a small heap chunk secret buffer. Then we create an entry in the proc file system. Then our userland program can use open and read to interact with this entry secret. After that, that's init. So then when we do a read to that, what we'll do is we're going to copy the secret from the kernel global object to the kernel heap buffer. We're not really copying this back to the user space, right? We're still just copying things in the kernel. So it's supposed to be secure. So next week, we will say how we can steal this. Even if they're just copying the buffer, we're going to steal this. We will be able to get the secret from the usernet program. Any questions for this piece of code? Okay, so that's for Meltdown. So next week we will get deeper. Today, I just want to give you a high-level idea on Meltdown and Spectral because those can get quite complicated. So I spent 2 weeks on this one. So the next attack is called Spectral, and this is related to another feature. This feature is related to out of order execution, but it's built on top of that. It's called speculative execution. So basically, the processor can preserve its current register state and make a prediction as to the path that program will follow. So out of order execution will execute instructions out of its original order, but it doesn't handle, let's say there is a branch. So what to do? So speculative execution handles the branch prediction. It will not execute. So before that instruction is really executed, before that predicate for the branch is really calculated, it will guess what branch it will take, then start executing there. Because maybe before there was a instruction stores or other instructions, so it will have out of order execution, but when it reaches out of order, it will predict what to execute. So if the prediction turns out to be correct, then the results of the speculative execution are committed or are yield. So this will create a huge performance bonus, right? Because you didn't waste your CPU for waiting the instructions. So it's a huge performance bonus. However, the prediction may be wrong. So when the prediction is wrong, the CPU should abandon the work it performed speculatively by reverting its register state and resuming from the correct path, right? That's how the CPU works. So the modern CPU's experiments find out that the speculative execution can run several hundred instructions ahead. So we're not talking about several instructions, several hundred instructions. So you can imagine that will make your CPU much faster. This is a very, very useful optimization. However, there is a problem of this feature, is that when the CPU revert its register state, the previous CPUs, they do not revert the cache. So the cache will stay as where the run path executes. So the run path bring some data into the cache. It will stay there. It will not be evicted, because I mean if you evict that, that also costs time. So the CPUs do not evict that, and that leaves a huge problem here. So here is the Spectral version 1. Spectral version 1 looks like this. It's basically a conditional branch misprediction. So let's say X is a variable and array size. Then if X is less than the array size, then we are going to retrieve the X as index from that array. Use that as an index for array 2 and retrieve the data to the Y variable. So if X is inbound, so the CPU will make some prediction here, right? Because here we have a predicate. Let's assume X is inbound. Then if the CPU predict the predicate is true, then the CPU will keep executing this statement, even if the result of this, before we know X is smaller than array 1 size or not. We don't know the result yet, but CPU will predict X is smaller, then CPU will start executing the second statement here. So that's out of order execution and also speculative execution, because we execute this one before this one, and when we execute this one, we are actually making a guess there, right? So if X is inbound and if it's correct, then you can say this will be very fast. Before we know the value of X, we also retrieve the value back to Y. And when we know the value of X, we just commit, the CPU just commit, then it's very fast. If it's not correct, then we have to revert this one. So this one will be slow. If the CPU guess this one is not inbound, then it will not execute this one. However, if it is inbound, then it has to execute this 9 again. So the second, this is called the conditional branch misprediction. The second version of Spectral is indirect branches prediction. So in this class, we have been talking about indirect branches a lot. We're talking about those instructions like call EAX, jump EAX. Those are indirect branches because at compile time, you don't know the value of EAX. However, the CPU will try to guess. When there is a call EAX, the CPU will try to guess what the value of EAX will be and start executing from there. If the guess is correct, then obviously the CPU made a very will get a huge performance boost, right? If you do not do that guess, the CPU just waits there, then a lot of CPU units will be wasted. So those are the two cases of spectrum. Next week we will see more examples. So by comparing those two attacks, we can see that Meltdown doesn't use branch prediction. Meltdown only use out of bound execution. Meltdown exploits a vulnerability specific to many Intel and ARM CPUs. So AMD CPUs were not really affected much, I remember. So Meltdown accesses kernel memory from user space. This access causes a trap. But before the trap is issued, the instruction that follows the access can leak the content of the memory through the cache cover channel. So that trap or that exception is what the CPU is designed to do. However, before the trap, the information is already leaked. So the researchers design that smart way to leak the information through the cache side channel before that exception. So those are the high level discussion of Spectrum and Meltdown. Any questions so far? So Victoria, you're saying you never heard of it. You mean Spectrum and Meltdown?
Yeah, when you asked if anyone had heard of it.
Okay. Okay, cool. So next week we will look at the details of Spectrum and Meltdown, and hopefully today I gave you some high level ideas there and also some background knowledge. So next week you will be able to understand what's going on. So this week's homework, I believe it's simple. You just need to do the 2 heap exploitation. Then after that, you just need to do LS CPU to show us the CPU you are using and do some calculation to figure out the sets and the weights of your CPU has. Okay, cool. If no other questions, we will stop here. See you guys next week. Hopefully next week we will do this in person.
Have a good day.
Thank you.
Okay, thank you guys.
Thank you.